Hello APC Mechanics students in Unit 2 Newton's Laws of Motion, Class 4 Newton's Second Law Part 1, then Section 1 Newton's Second Law of Motion. A box is placed on a smooth level surface and acted by two balance forces. Remember that whenever the surface is smooth we have no friction, and it's being acted by two horizontal balance forces given by 20 newtons. The box will preserve its state of motion either at rest or uniform motion constant velocity, and this is because it's being acted by balance forces 20 newtons, and we have the pull of gravity is equal to the normal push exerted by the level surface. Now suppose the right force is increased to 35 newtons. This increase will cause the box to accelerate by a net amount given of the difference between 35 and 20, which is basically 15 newtons to the right. However, we cannot equate force given by newtons by acceleration meter per second squared. This requires to implement a law. Then basically the difference between 35 newtons and 20 newtons would cause the box to accelerate, but this 15 newtons cannot be equated directly by acceleration. We need to implement a law. Newton's second law of motion states that unbalanced net external forces causes a body to accelerate. The value of this acceleration is the product of mass and acceleration. Mathematically can be represented by the net force is given by m multiplied by the acceleration, or the sum of forces given by ma. Given that this is a vectorial equation which requires a decomposition along a dimensional space in an xy coordinate system, it gives the birth to two linear equations, as we shall see. The main feature of Newton's second law is offering a neural bridge between the cause and the evolution of the system. Now example 1, let's calculate the acceleration of the block given that its inertia or mass is given by 950 grams. Now the first thing that we should do is represent, using the technology of the FBD, the different forces acting on the box. We have the pull of gravity down, balanced by the normal push up. We have the horizontal force F1 acting to the right by 35 newtons, and the horizontal force F2 acting to the left by 20 newtons. And notice that on the FBD, I have represented in length to be F1 greater than F2. Now we're ready to implement a Newton's second law given by F net is ma, and F net would be replaced by all the forces acting on the box that they are represented on the FBD. We have the force F1 plus F2 plus Fg plus Fn, and here we're adding them vectorially without caring about the direction of these forces. And remember that this m represents the mass of the object given by 950 grams, along which we're applying Newton's second law, and a would be the acceleration. And we know that whenever we determine the acceleration, the problem is done. Why? Because by determining the value of a, we can define the system kinematically or via calculus approach. Now we're gonna project this equation. So as we said previously, this equation would give the birth of two other equations, and this is done by projecting it either along the horizontal or along the vertical. Along the vertical won't give us any information because the pull of gravity would be balanced by the normal push in this case. For this reason, we're interested in projecting it along the horizontal. Now along the horizontal and taking the positive direction to be to the right, so F1 is completely along the right direction, so that would be plus F1. F2 is acting completely along the negative direction, so that would be minus F2, whereas Fg and the normal push has no projections along the horizontal. And in this case, we are searching for the value of A. Then if we isolate A is given by F1 minus F2 divided by m. The value of F1 was given by 35, F2 by 20. And here, so let me change this mass to be 900 grams. So converting 900 grams into kilograms, that would require us to divide by 1000, and that would be 16.67 meter per second square. Now section 2, acceleration of a free fall. We know that a free falling object has an acceleration equal to g, but at this point we didn't provide any proof why for a free falling object the acceleration is equal to g, and this can be proven using Newton's second law. Consider an object in free fall. Remember that whenever an object in free fall, the only force acting on the object is the pull of gravity. A resistance must be neglected. The forces acting on the object are simply the pull of gravity, which is down. We don't have a normal push because the free falling object is being not supported by any support. And now we can apply Newton's second law of motion. Remember that the net force would be replaced by the total forces acting on the body, and in this case it's simply given by the pull of gravity. No need here to add any other force because we don't have. And now we're gonna project that along the vertical. Let me assume that the positive direction is down. That would be Fg is ma, and Fg would be replaced by plus Fg since the positive direction is down. And we know that Fg can be upgraded into mg. M and M cancel, and simply the acceleration would be given by g. And by that we have proved that the acceleration of a free fall body is simply given by the gravitational field strength g. Now section 3, acceleration on a smooth ramp. We will investigate the expression of the acceleration of an object sliding along a smooth ramp. This can be done using Newton's second law. Consider an object sliding down along a smooth ramp inclined by theta. So here we have a box. The ramp is considered to be smooth, then we will neglect friction. Then what are the forces acting on the block? Let me repeat and say we are interested in finding the acceleration of the block. This block will accelerate downward due to the pull of gravity. Previously, for a completely free fall, the acceleration is given by g. In this case, we need to check the modification of the acceleration when it is sliding down without friction on an inclined plane, which is basically ramp. Now the first thing that we should always do in order to implement Newton's second law, we need to represent the FBD. And here I'm representing the FBD in this shifted way. Why? Because box is being placed on a ramp, so that would represent the positive x-axis and that would represent the positive y-axis. Now we have the pull of gravity, which is down. We have the normal push, which is up the ramp, and in this case it's up left. Now we're ready to apply Newton's second law of motion given by F net is ma, and remember that F net should be replaced by all the forces acting on the block. In this case is given by the pull of gravity and the normal push, and we will represent them vectorially without caring about the direction. Now we need to determine the acceleration, and remember that the block is only accelerating along this x direction. For this reason, I will say along the x-axis. We're gonna project it along the x-axis. So we need to specify the angle that the pull of gravity makes with either the x or the y. So we know that at this stage that theta would be the angle between the pull of gravity and the y-axis, and this can be decomposed into two components. Since theta is the angle with the y-axis, that would be Fg cosine theta, and that would be Fg sine theta. For this reason, whenever we're doing along the x-axis, Fg would be replaced by Fg sine theta. The normal push has no projection along the x-axis, and A would be completely transformed into A, because that would be the total acceleration along the x-axis, and we don't have any acceleration along the y-axis. And that would be mg sine theta. M cancels with m, which means that A would be given by g sine theta. And as you can see here, the modification for a free fall, the acceleration is given by g, whereas for an object sliding down along frictionless ramp, it would be modified by a coefficient given by sine theta. And remember that sine theta has no dimension, has no unit. So if this is meter per second square and this has no unit, then the unit of g is also given by meter per second square. So remember that equations in physics, left members and right members should agree in terms of unit. Then the acceleration of a body sliding on a frictionless ramp is given by A, which is g sine theta. Now section 4, acceleration on a rough ramp. Now we're gonna switch friction on, and we will see how that would affect the expression of the acceleration. Then without friction, the acceleration is given on a ramp, frictionless ramp, given by g sine theta. We would see how this would be modified whenever friction is on. This can be done eventually using Newton's second law. So here we have a ramp inclined by theta, and the ramp in this case is rough. Now, first of all, since we're talking about motion, or let me say first, whenever we say friction, we can distinguish between two types of friction: static friction, kinetic friction. Since we're talking about motion, then we're interested in kinetic friction. All right. What are the forces? So as we say always, the first thing that we should do is proceed with an FBD. We have the pull of gravity down, we have the normal push up left, and we have the friction. Since the motion is down, then the friction is gonna be upright along the ramp. Now we are ready to apply Newton's second law, and F naught would be replaced by all the forces acting on the object given by the pull of gravity, friction, and the normal push. And notice that here we have added them vectorially without caring about the direction of each force. And now, because we are interested in determining the acceleration along the x-axis, which is taken to be the ramp, so we're gonna say along the x-axis, and the pull of gravity would be making an angle theta with the y-axis, then that would be theta. And in this case, Fg would be replaced by Fg sine theta, Fn has no projection, and the friction would be replaced by minus Ff, because we're assuming that the positive direction would be down. And we're interested in determining the acceleration. However, here, if you notice carefully in this equation, we have two unknowns. We have A, which is to be determined, and we have the friction also should be determined. We know that the friction is given in this case to be the coefficient of kinetic friction multiplied by the normal push y, kinetic and not static, because as we've mentioned that the block is moving. And in this case, we know that the normal push would be given by, on a ramp from the previous class or video, is given by Fg cosine theta. And this can be proven again by considering now the y-axis. And here you can see the fact that whenever we're solving for a vectorial equation, we make use of both the x and the y direction, or the vertical and the horizontal. Then along the y-axis, we can say that the normal push would be balanced by Fg cosine theta, which is the y component of Fg, and this is because they are balanced forces. There is no motion along the y-axis. So now this can be replaced here, because we know what is Fg and what is cosine theta, and eventually friction would be given by mu k. So if you notice carefully, this would be replaced by Fg cosine theta, then the friction is given by mu k Fg cosine theta, and this can be replaced here. So we have Fg sine theta minus mu k Fg cosine theta. Now Fg can be replaced by mg, and here we can cancel this mass with this mass with this mass. Notice that we should cancel the mass here and the mass here, because these two terms are separated by a minus sign. If this is replaced by a multiplication, then it's sufficient to cancel one of the masses. And in this case, the modification of the acceleration is given by g sine theta minus mu k g cosine theta. In order to understand more, we can factor out g, and the acceleration along a rough ramp would be given by g as a factor sine theta modified by this term mu k cosine theta. And here notice that all the units are in agreements. Why? Because this has no unit, this has no unit, and we know that the coefficients for friction, both types, are unitless, which means that this is meter per second square as a dimension, which agrees with the unit of the acceleration. Then the acceleration of a body sliding along a rough ramp is given by g factored sine theta minus mu k cosine theta. And now we can do for section 5 the following summary, which is beautiful, and let me explain why. We're talking about specific dynamical systems given by free falling body sliding on a frictionless ramp, or body sliding on a rough ramp. In the case for a free fall, it's given by g. If it is sliding without friction on a smooth ramp inclined by theta, then it would be modified into g sine theta. And if it's sliding on a rough ramp, sine theta will be modified by a term given by minus mu k cosine theta. And now we are ready to solve some exercises related to what we have explained previously. A block of mass 3 kilograms. Why at this stage the mass is important unlike unit 1? Because Newton's second law is directly related to inertia, which is mass. Initially at rest, which means that the initial speed is 0, is pulled along a frictionless horizontal surface with the force shown as function of time t by the graph above. So in this graph, if we have the value of the force, we can determine the value of the time. If we have the value of time, we can determine the value of the force. The acceleration of the block at t given by 2 seconds is, so here we suppose that the block is being placed on a frictionless level surface. Then what are the forces acting on the block? We have the pull of gravity down, balanced by the normal push up. We have the pulling force, which is horizontal, given by capital F, and it's frictionless, no need to worry about friction. And we need to determine the acceleration of the block at t is equal to 2 seconds. So specifically at t is equal to 2 seconds, the value of the force is given by 4 in newtons. Then we know that F is given by 4 in newtons, and now we can apply Newton's second law given by F net is ma. And what are the different forces acting on the block? We have the pull of gravity plus the normal push, we need to include them all, plus capital F given by ma. So let me suppose this is the positive direction of the x-axis or the horizontal. So along the horizontal, we would say that this would be replaced by 0. Now we drop down all the vectors, and each vector will be replaced by its component, that would be 0. And capital F, it's completely horizontal, no need to project it, and it's acting in the positive direction, that would be ma. No need to project the acceleration, we're interested in determining the value of a. Then if we isolate a is given by capital F divided by m. Capital F is given by 4, m is given by 3 meter per second square, which makes b to be the correct answer. Now exercise 2, a skier is traveling down a slope that is inclined 30 degrees above the horizontal. So let me do a sketch. This is the ramp. Now this is 30 degrees, and that would be the object or the skier. The coefficient of kinetic friction between the skier and the slope is given by 0.1. Which of the following best describe the acceleration of the skier? We know that this is the case, so always a would be proportional to g, because we're talking about a slope that would be sine theta. Because we have friction, then it would be minus mu k cosine theta. And if this is an MCQ, and if you remember directly the formula, you can plug in the numbers and it would be given by b. But here let me provide here an explicit solution. So let me say F net is given by ma, but in order to solve this equation we need to provide the FBD. So this is the ramp or the x-axis, that would be the y-axis. The pull of gravity would be down, that would be the angle 30 degrees, and the normal push is upright, and the friction would be up left, opposite to the direction of motion. And now we can say that we have the pull of gravity plus the normal push plus the friction is given by ma. And now we can say along the x-axis the pull of gravity would be replaced by, if 30 degrees is the angle with the y-axis, then along the x-axis it would be given by fg sine 30 degrees. The normal push has no projection along the x-axis, whereas friction would be replaced by minus ff, because it's completely acting along the negative direction. And remember that acceleration would have no projection. Fg would be replaced by mg sine 30 degrees, mg with sine 30 degrees. Now what about the force of friction? It is unknown, but we know that it's related to mu k fn. And remember that fn would be given by fg cosine theta, because they are balanced forces along the y direction. Replacing this here, that would be mu k fg cosine theta, which is basically mu k mg cosine theta. So that would be mu k mg cosine 30 degrees given by ma. Now here m with m cancels, then a would be given by g sine 30 degrees minus mu k g cosine 30 degrees. And if we factor out g, that would be the same expression that I posted at the beginning of the exercise. Now exercise 3, a block of mass m is accelerated across a rough surface by a force of magnitude capital F that is exerted at an angle phi with the horizontal as shown above. So basically the horizontal component of F is pointing right, then it's gonna move toward the right opposed by friction because this is a rough surface. The frictional force on the block exerted by the surface has a magnitude F. What is the acceleration of the block? Always and forever at this stage, acceleration is determined by Newton's second law. F naught is ma, where m is the mass of the block. F naught would be all the external forces acting on the block. A would be the acceleration of the block, and in order to make use of this equation we need to do an FBD. So we have the pull of gravity, which is down, we have the normal push, which is basically up, we have F making an angle phi with the horizontal, and we have the friction, which is completely to the left. And remember that at this stage we don't draw any components. However, if you draw here components, it's fine because this is an MCQ, no need to provide any solution. Then let me write down all the forces. That would be F vector plus the normal push plus the pull of gravity plus the friction, and here we can place the forces in terms of vector, no need to worry about any direction. Are we interested in doing that along the horizontal? So capital F would be replaced by the horizontal component given by F cosine phi. Normal push has no projection along the horizontal, as well as for the pull of gravity, friction would be completely to the left, and that would be given by ma. We're interested in determining the expression of the acceleration. Acceleration would be given by F cosine phi minus F divided by m. Notice that I have kept the friction as it is without referring to the definition mu k Fn, simply because all the choices are given by friction, and in this case the correct answer would be E. Exercise 4, a block of mass m is accelerated across a rough surface by a force of magnitude capital F that is exerted at an angle phi with the horizontal as shown above. The frictional force on the block exerted by the surface has a magnitude small f. What is the coefficient of the friction between the block and the surface? Now we need to find the coefficient of the friction. Here we're talking about kinetic friction because we suppose that the block is moving simply because they have mentioned it is accelerated. We know that friction is given by the coefficient mu k multiplied by the normal push. We are interested in determining mu k. Then mu k is given by friction divided by the normal push. If you refer to the choices include F, but we need to search for the value of the normal push. The normal push can be determined by considering Newton's second law along the vertical. For this reason, I'm gonna say F naught is ma, and I will refer to the same FBD that we have done in exercise 3. We have the pull of gravity, we have the normal push, we have the force F making an angle phi with the horizontal, and we have friction acting left. So that would be normal push plus the pull of gravity plus capital F plus small f, which is ma, and I will consider this equation along the vertical. So that would be pull of gravity is acting down, which is minus, the normal push is acting up. However, if you notice that this is basically, we have done it in the previous videos. The normal push can be directly determined as a shortcut. Since this is an MCQ, we can say that the normal push would be the pull of gravity plus a modification term. This would help the normal push, so we must decrease it by a value of F sine phi. That would be the expression of the normal push, which should be replaced here in this fraction. However, let me continue here. Plus, so F sine phi, that would be the vertical component of this force, plus the friction, which is 0 along the vertical, and that would be 0. So usually we used to do this in another way, and we used to say that simply we have the pull of gravity. So let me say another method. We used to say the pull of gravity is down, balanced by the normal push, which is up, with F sine phi, and we're searching for the normal push to replace it here, and that would be the normal push, which is mg minus f sine phi. Now we can replace it. That would be mu k is f divided by mg minus f sine phi, and the correct answer in this case would be E. Now exercise 5, a block of mass m is sliding down an inclined plane that makes an angle theta with the horizontal as shown in the figure. The coefficient of kinetic friction between the surface and the block is mu. Which of the following is the correct expression of the acceleration A of the block? For a free fall it's g. For an object sliding without friction on a ramp is g sine theta. For a rough ramp that would be g sine theta modified by the term minus mu k cosine theta. In this case D would be the correct answer. Exercise 6, a small sphere hangs from a string attached to the ceiling of a uniformly accelerating train car. It is observed that the string makes an angle 30 degrees with the vertical. This is the vertical. That would be the angle 37 degrees. The magnitude of the acceleration A of the train car is most nearly, so we need to find the acceleration of the train. The acceleration of the train would be equal to the acceleration of this small sphere, since they are all connected together, and we know that the acceleration of the sphere can be determined by considering Newton's second law. And in order to solve for a Newton's second law, we need to represent its FBD. So we have the pull of gravity, which is down, and we have the tension that is along the string. No need to do any projections at the level of the stage. Now this is another vertical. If this angle is 37 degrees, then this angle would be 37 degrees as well. And now we're gonna say, apply Newton's second law given by F net is ma. What are the different forces acting on the sphere? We have the tension force, we have the pull of gravity given by ma. And now let's start with the projection along the horizontal. So that would be Ft, which is acting in the positive direction. So the vertical component would be cosine 37 and the horizontal would be sine 37. Now Fg has no component along the horizontal. That would be 0 given by ma. So Ft sine 37 would be given by m multiplied by a, but notice that here we have two additional unknowns given by the tension force and given by the mass. For sure, now we need to refer to the vertical equation. So along the vertical we don't have any acceleration, so it's only accelerating horizontally. So we can say that the pull of gravity would be balanced by the vertical component of the tension force given by Ft cosine 37. So mg would be given by Ft cosine 37 degrees. So let me search for the value of Ft. So Ft in this case would be given by mg divided by cosine 37. And now let me try replacing this here and check if it solves the problem. That would be mg divided by cosine 37 multiplied by sine 37 is given by ma, and luckily m with m cancels. Sine 37 over cosine 37 give us tangent 37, then a would be given by g multiplied by tangent 37, and this is a remarkable expression, so can be generalized. Given by a is g tangent theta in this case, and if you plug the value of g to be given by almost 10 and tangent 37 in degrees, then the correct answer would be given by 7.5. Now exercise 7, which is the exit ticket of today's class. A block of mass m is pulled across a rough surface. Rough means we have friction at a constant speed. This is very important. We don't have acceleration. Constant speed means that the acceleration is 0. All forces along the horizontal and the vertical are balanced by a force of magnitude capital F, which acts at an angle theta to the horizontal, as shown above. The coefficient of kinetic friction. Now here pay attention. Although the acceleration is 0, but we have motion, and whenever we have motion, then the friction is kinetic. Okay, so don't think about kinetic friction is related to acceleration. Kinetic friction is related to the state of motion, or friction can come in two flavors based on the state of motion, whether we have motion or no motion. And as we know that motion has several types: constant acceleration or zero acceleration. Here we're the case in the zero acceleration. So we need to determine the coefficient of the kinetic friction. Coefficient of kinetic friction basically appears in the definition of the friction given by mu k multiplied by Fn. We need to determine the expression of mu k. Then mu k is given by Ff divided by Fn, and here if we refer to the choices, neither Ff nor Fn appear, which means these need to be replaced by referring to Newton's second law or to the balance forces. We can say that along the horizontal, so let me draw the FBD. We have the pull of gravity, we have the normal push being up, we have capital F making an angle theta with the horizontal. So along the horizontal we can say that, and remember that. So how do I know that I have forgot friction? Because it is moving at a constant speed, which means it should be balanced by the friction which is to the left. Then we can say that Ff would be equal to F cosine theta, which is the horizontal component of capital F. So that would be basically F cosine theta. Now what about the normal push? In this case you can directly say the normal push would be the pull of gravity given by Fg. With a modification term, this would decrease the normal push given by F sine theta. So that would be along the vertical. We have the pull of gravity being balanced by the normal push which is up, and F with theta. So F plus, so this is the normal push plus F sine theta, and we're interested in finding the normal push. Then the normal push would be given by the pull of gravity, which is mg minus F sine theta, and we can replace it here. And in this case the correct expression would be given by E. Then that's it for me in this video, guys. See you soon in a new one.